Today we're going to be working on the second derivative test so we can determine the concavity of the function f and also to see if there's a point of inflection in our graph. So f of x is equal to x cubed minus 12x minus 5. We will need our second derivative, so f prime of x is 3x minus 12, and the second derivative would simply be f double prime of x equal to 6x. So since we're using the second derivative test, we're going to get our critical number from the second derivative. So we simply equate 6x to 0. So x is equal to 0. So since this is our critical number, we can use our sign chart. And now our sign chart has a different purpose, and not to determine the local extrema or the behavior of the increasing and decreasing function, but to find and determine the concavity and the point of inflection of our function f using the second derivative. So we need to set a value for x here. Let's use -1 because -1 is less than 0. So we'll have 6 times -1 because that's the second derivative, 6x, and we'll have -6, which gives us a negative value for the second derivative. And for the next interval, we'll set the second derivative to +1 since 1 is over 0. 6 times 1 is 6, which is a positive value. So since we are using a different, or you are using the sign chart on a different purpose to determine concavity, it's basically going to, or the sign of our second derivative will help us determine the concavity of the function. If it's negative, the function f is concave down, and if we have a positive value for the second derivative, we have concave up. So for our analysis, f, or function f, is concave down on the interval -∞ and 0. Or we can write it out as x less than 0 since f double prime is negative. And for our concave down, at 0 to +∞, or we can write it out as x greater than 0 since f double prime is positive. Now, another condition about concavity is when you have concave down or concave up, or opposite concavity in a given critical number, you are going to have a point of inflection for your function f. So POI, or point of inflection, exists at x equal to 0 since f double prime is changing from negative to positive. So this is now our analysis for function f of x using second derivative, and we're able to identify where the concavity of the function f is, and also if the point of inflection exists in a given function using the second derivative test. Now let's answer problem number 2. For problem number 2, f of x f prime of x is 5x to the 4th minus 80, and f double prime of x is equal to 20x cubed. So from our second derivative, we'll set it to 0 to find our critical number, and 20x cubed equal to 0 will give us 0. So the critical number for our second derivative will be 0, and this is what we're going to be using in our sign chart. So let's see if the concavity is positive or negative, or concave up or concave down on this interval. So let's start with the left interval. So let's use f of -1, and our f double prime is 20x cubed this time, so it's 20 -1 cubed, which gives us 20 times -1, which is -20. So our concavity for the interval for x less than 0 is negative, and for f double prime of +1, we'll use 20 of 1 cubed, and f double prime of 1 is 20 times 1, which is +20. So the concavity is positive for x value greater than 1. So just like what we did on problem number 1, f is concave down on the interval -infinity and 0. F is concave up on the interval 0 and infinity, and POI exists since f double prime changes from negative to positive, and it exists at x equal to 0. And if you want to change it into an ordered pair, so we'll have simply 0, and f of 0 is 100. So that is your point of inflection, and this is our analysis for the function f using the second derivative.